is to make appropriate, I guess, inferences about the population. And so inferential statistics will pretty much be the remainder of the stuff we talk about. We have about 5 sections left, 2 chapters, and it's all on types of inferential statistics, taking samples, information about samples, and generalizing to populations. So each chapter is going to deal with a different type of inferential statistics. There's estimation and hypothesis testing. And we're talking about estimation in this chapter. We'll talk about hypothesis testing in the next chapter. And so what we're doing with estimation, so we're studying estimation here. Well, as you would imagine, we're going to estimate the value of unknown parameters. Now remember, a parameter, there's a parameter and a statistic that we talked about in the very beginning of the semester. A parameter refers to a population. Statistic refers to a sample. So when they say unknown parameters, they're saying unknown values about the population. And notice how they use mu and p. That's the population mean and the population proportion symbolism that we've used throughout this class. But in this section in particular, we're going to look at the population proportion as represented by the section name. We're going to look at population proportion here. Next section, we'll look at population mean. And well, really what we're going to do is start off with these generalities. We'll start off with really more so looking at estimating in general before we look at population proportion specifically. So in general, for estimation, we generally want some sort of point estimate, which is really a starting point. It's the value of a statistic that estimates the value of a parameter. So this would be, so statistic refers to sample, parameter refers to population. So a statistic would be some value you find about the sample, and you think, all right, this number seems good enough. Let's maybe apply this to the population. So, for example, I use this example every time. I figure out everybody's heights in here. I figure out the average height. And so that would be a sample height. You would all be the sample, and Southeastern would be the population. So I'd say, all right, the average height for students in this class is however many inches that comes out to be. And I'd say, all right, that would be a point estimate if we were to say, well, maybe that is a good characterization of the average height of students at Southeastern. We use the height of people in this class. Is it a good estimate? That's an arbitrary thing. It may or may not be, but it would be a point estimate if we make such an assertion. Now, another example of a point estimate is something we actually talked about the last section when we introduced this p-hat notation. And when we dealt with proportions, it's normally a very quick fraction. It's the frequency that somebody shares that characteristic divided by the total number of people. It would be a proportion. So the proportion of men in this class, just 1, 2, 3, 4, 5, 2, 3, 4, 5 out of however many there are. Let's just say there's 10 of you in here. And so 5 out of 10 would be the amount of men in this class. So something very simple like that. But the problem with just looking at point estimates, so just getting one concrete number, well, we could get one number from one sample. So in this class, I figure out the proportion of men to total number of people in the class. But what about if I go to another class and I do the same thing? It'd be much different. If I go to an engineering class and I do that for engineering, it's going to be predominantly males. But if I go to nursing and do it for one of their classes, it's going to be predominantly females. So these might not be very strong indications of generality because there's all this variability, as in statistics vary from sample to sample. So really, we don't want just a singular number, a point estimate, but rather we want an interval that sort of encapsulates possible values that we could get. And something we also add to this interval is something called a level of confidence. So really, in this section, we're going to be looking at a confidence interval and a level of confidence for that. These are two very important ideas in statistics. As you would imagine, a confidence interval, in layman terms, is an interval you're confident about certain values falling within. This interval is due to the variability of measurement in general. The average height for this class might be a certain amount of inches. The average height for the next class might be a certain number of inches, and for the next class, and the next class, and the next class. But we would hope that those averages would fall within an interval. And we would say, all right, I'm pretty confident that the average height will fall within this interval. So on the assumption that we have a point estimate, so the point estimate gives us a starting point, and this interval is characterized, so a point estimate, think about that as something, say in the middle, and then the interval around that would be the margin of error, or how do things deviate from the point estimate. You might think of this similarly as a mean and a standard deviation. It's the same concept. So a confidence interval consists of an interval of numbers based on a point estimate. So you take a point estimate, a point that you start at, and then you find some interval around it. And really it's not really too much of a formula, it's more so intuition. You find this amount of error that's involved. When you add the error to the point estimate, you get a larger value, and when you subtract that error from the point estimate, you get a smaller value. The larger and the smaller, they give you your interval, which encapsulates the point estimate. There's also something called a level of confidence. How confident are we in this interval? Well, it turns out we can give it a specific, well, in statistics, we want to give this a specific percentage. So you could, normally the terminology is, we are 95% confident that the intervals will fall, or the values will fall in this interval. And this level of confidence, we normally use this formula backwards. But basically, this formula is a complement, 1 minus a percentage generally. And we'll see what this formula, how to use this formula here momentarily. But these are the general ideas, and none of this has anything to do with population proportion quite yet. This is just in general for estimation. So generally, we need a point estimate, a margin of error, and a level of confidence. And with those three things, we can do a lot. We can make a lot of assumptions about collections of samples. So let's think about what this means. So I have example 1 at the bottom here, while keeping the definition up here. If we have a 90% level of confidence, so one way this can be interpreted, if you have, let's say you take 100 samples. Let's say we interview 100 classes about their heights. So 100 different classes, and we could figure out 100 different confidence intervals. Not only a point estimate, but a confidence interval as well, based off of each sample. Then, as you would imagine, if it's 90% confidence, then we expect 90 classes to include the parameter and 10 to not include the parameter. So what this is saying is there is an actual population height, average height of this whole university. Let's say we don't even know what it is. Whatever this average height of university students is right now, however you classify what a student is, let's say there is one. We want to understand what that number is based off of finding samples for each class. Now, the thought process is if we interview 100 classes and construct an interval based off of each class, not only find a point estimate, but an interval, then a 90% level of confidence means that we expect 90 of 100 classes to have this true university average height included in their interval. So that's one way we can interpret this. Really, the computation comes down to just 90 and 10. It's not really computational, it's more just conceptual. So let's look at something a little bit more concrete or something a little bit more hands-on here. So let's go ahead. So everything we've talked about so far does not pertain to the population proportion, which is the namesake of this section. So far, we've talked about generalities of the chapter as a whole. Now let's turn our attention to population proportions. So we already I mentioned in an example above. So for the population proportion, we generally need three things here: the point estimate, the margin of error, and the level of confidence. Pretty much all the different things that can be found in this little definition here. So we can make a lot of interesting assumptions about the population. Well, we have the point estimate for free. The point estimate is the formula we talked about in the previous section. It's the frequency of students or just objects in general that possess a certain characteristic divided by the total number of occurrences. So if we are given the lower and upper bound, so we'll work this out incrementally. Let's say we are given the lower and upper bounds of around a point estimate. And let's see how we can work out other values by us being given these values. So in example 2, they give us the lower bound and they give us the upper bound. This characterizes the interval here, the confidence interval. So they're telling us the lower bound and the upper bound, and they're telling us that they found 1,000 samples. So let's go ahead and determine some of these other values here based off of those. Now, in example 2, it starts off by asking the point estimate. Well, the problem here, they don't give us an X, but they do give us an N, but they don't give us an X value. But this is actually okay. So normally how this works visually is the point estimate is right smack in the middle. The lower bound is equally to the right, and the upper bound is equally to the left. Or switch that. Lower bound to the left, upper bound to the right. And it's equidistant, as in the same distance either way. And this is just true in general. This isn't a population proportion thing. This is just, if you have an error, you add that to the point estimate, you subtract that to the point estimate, from the point estimate. In other words, what I'm trying to say is that you can figure out the point estimate if you're given the lower and upper bounds by finding the average of the two bounds. It's the average. It's right smack in the middle. You have a lower bound, you have an upper bound. Your point estimate, which is your central point, has to be right smack in the middle. So again, this is pretty easy of a computation. let's go ahead and figure out that number real fast. 0.215 plus 0.485, 2. So we get about 0.35. Again, we couldn't really use the formula where we have x divided by n because we weren't told x. In fact, you might notice in part C has us find x. So kind of foreshadowing here. Part B wants us to determine the margin of error. Now the margin of error, so we know what so this is what we found. We just found the middle point. We know what the smaller point is, the lower bound of our interval, and we were also given the upper bound. That's what we found. Now, intuitively, and I'll ask you all this, does anyone happen to see the computation for finding the margin of error?
Will it be 0.35 minus 0.215?
Yeah, that's it. That's all there is to it. And in fact, there's two ways you could technically solve for it. The margin of error is literally the difference between, well, really any two of these, or between the point estimate and the upper bound. So same thing. You should get the same exact number because you know that the error is applied equally in both directions. So you'll get the same number. I'll just take that the error is 0.35 minus 0.215. Again, if you do 0.485 minus 0.35, you get the same exact number, or you should. So let's figure out what that is real fast. Oops. 1.5. So far, that's it. And then part C wants us to determine the number of individuals in the sample with the specified characteristic. Here they are asking for, they're asking for us to find X. As in, they're kind of wanting us to work backwards from this formula. Because X, from the formula that when we define this, P with the hat was the sample proportion, or the sample proportion in this section is the point estimate. X is the number that have a certain characteristic, and N is the total number. Well, the good news is this is just quick algebra. This is a very quick algebra problem because we know P with the little hat on top is 0.35. X is, well, we don't know. But little n, they actually gave that to us in the very beginning of the problem. Sort of just slipped under the radar. It's 1,000. They gave that to us in the very beginning of the problem. So really, it's just 0.35 times 1,000, which is 350. 1, 2, 3. Okay. 350, that's it. So out of 1,000 people, 350 of them have whatever this characteristic is. So we kind of worked backwards here. And this is what we can do if we are given the lower and upper bounds. In practice, we're normally not, but this just goes to show how far we can go if we are given the bounds. You could figure out the point estimate. You could figure out the margin of error. And you could even figure out this. The number of individuals that share a characteristic. Does anyone have any questions before we move on? So hopefully this stuff's fairly straightforward so far. One thing I wanted to note, though, I didn't put this in my notes, and it is a question on the homework. It really asks you for a population proportion, what type of variable do you need? and it asks you, do you need a qualitative variable, a quantitative variable? And this is specific for proportions. Now, proportions is you count a bunch of stuff that happens and divide that by a total number of people. That's really more so categorical because it's really yes or no. So if I tried to make a category out of, or a proportion out of heights in this class, I mean, what would the proportion be? There needs to be a threshold. So you would have to ask how many people here are taller than 5'7", 5'7". So really, again, I didn't put this in the notes, but the type of variable you would need is qualitative. You need something categorical because with proportions, you count stuff, you count occurrences of stuff. And in particular, you need qualitative with two values, two outcomes. And as you could see in all of these problems, you could see this in each example, that in every example, we're moving down. So example 4, do you support the death penalty or do you not support it? Yes or no. There's another one that comes up. Do you watch football? Yes or no. Notice these are categorical with two values. So it is consistent, but I wanted to make that clear to everybody. That's if you see that homework question and wondering, what is that really asking? That's what it's asking. Just what type of that variable ultimately are you looking at in general? So let's see. 1 second. Okay. Does anyone have any questions? Doesn't seem like it. Okay, so the last example was on the assumption that we were given the lower and upper bounds. But what about if we're not given those, which is normally in practice what happens? Well, then that means we have to find the lower and upper bounds. But to find the lower and upper bounds, we need to know the margin of error. And there is a formula for finding the margin of error. And this formula is probably the hardest part of this section. So if you can put this formula correctly in your calculator, you will be fine. And we'll do 2 problems to make sure you can. So the formula is given here as, so I'm not sure how easy this is for all of you to see. I'll write it out a little bit larger. That is alpha divided by 2 as the subscript. That is as the subscript. I'll explain that notation in a second here. And if the P with the hats are hard to see, I'll rewrite them just a little bit larger. So what this formula is telling you, so we saw this notation before. In fact, if you look on your test, the test that I just handed out to everybody, I ask what that notation means on problem 13 of page 3. We've messed with this formula, or not formula, we've messed with this notation before. Number 13, page 3. And it ends up being the, it corresponds to the z-score when the area of the subscript is corresponding to the right. So really, I'm going to simplify this formula a little bit. I'm going to bring back something, the inverse norm. We talked about this briefly 2 sections ago, the inverse norm. When I reference that, I talked about it briefly on page 74 of the notes, the inverse norm. This will be the key to understanding this notation. But really, we are going to be taking the inverse norm. Let me make sure I write this down correctly. 1 minus alpha divided by 2. And I'll explain all of this in a second. What's alpha? I know it's weird at first. And then the square root stuff follows. There's a few reasons for all of this happening, and the way I'm writing it is the most simplistic way of thinking about it. So again, this calculator implementation, if you get this down, then this section shouldn't be too bad. But to compute the lower and upper bound, because this value that I wrote out does not give you the lower or upper bound. It gives you one number, and that's the error from the point estimate. Once you have that error, then you can add it or subtract it from the point estimate to figure out your lower and upper bound. So you're basically figuring out how far away do I have to go from the point estimate, and then you apply it. So it's kind of boom, boom, 2 steps. Now let's talk about an example where we have to apply this, and I'll keep the formula above while we talk about example 3. So they want us to construct an interval. So an interval being a lower and an upper bound. And they tell us that X is 540, N is 1100, and they also tell us that the confidence interval is 94. So generally they have to, normally they give you a confidence interval because the confidence interval helps you find out this alpha thing that we'll look for momentarily. Now, we need a few things here. If we look at this formula above, so that formula on the very top of the screen right now, it needs an alpha, a p with a little hat on top, and a lowercase n. Well, we know lowercase n, check. Cool. Let's go a little bit easier. We'll find the easier one, p hat. Well, they give us x and they give us n. They do not give us the lower or upper bound, so we can't find the point estimate that way, but we can find it by looking at 540 divided by 1100. And rounding within a problem is always weird to me. I'm going to just put a bunch of decimals. When you round within a problem, you don't want to round too early or you might screw up the problem. So I'm going to keep it like that. So in our formula, we have lowercase n, we have p with the hat on top. All we need is this alpha thing. What is alpha? Now they say something about whatever this means. There's a 1 minus alpha times 100% confidence interval. Now all this is a fancy way of saying that alpha is going to be, well, ultimately, what you're doing is your level of confidence that they give you, you're basically finding its complement, and you're looking at its proportion. So what's the complement of 94%? Just 6%. So really, you're looking at 1 minus 0.94, which is 0.06. That's alpha. It's the complement. But it's the complement as a proportion. That's all that's saying. I won't get into the algebra. There's a little bit of algebra. Won't even get into that. It's the complement as a proportion. That's alpha. Is everyone good so far? So we know all the values. So we can figure out the error, which is now z to the, well, the subscript here is alpha divided by 2. So that's 0.06 divided by 2. We'll get to that here in a bit. Square root of 0.490909 times 1 minus 0.490909. All of that divided by lowercase n. And so what I'm going to do is I'm going to put this into the calculator by using the equivalent form that I wrote on the top of the screen using that inverse norm stuff. If you plug it in exactly like that, you should be perfectly fine. This is what I'm going to do. And again, this is on, I think I said page 74 of the notes. You click on second and vars. So vars is over here. And that brings you to the distribution menu. From there, you should see inverse norm right here. Third one down. So again, that's second and vars. Vars is right underneath the bottom cursor here on your calculator. There should be. And you should see distribution up top. So when we did inverse norm before, it needed 3 parameters. It needed 3 numbers. But we are on a very specific assumption here. So all we're going to do is give it 1 number, just like how I have it written up on the top of the screen here. 1 minus alpha over 2. We found alpha to be 0.06. 0.06 divided by 2. Close off the parenthesis because we found alpha to be 0.06. Now, this would give us the z-score. The z-score for having an area to the right, that is 0.06 divided by 2. So that's what this notation means to the right. But since our calculator is programmed to find to the left, that's why we're subtracting from 1. But in summary, though, basically, as long as you follow my little calculator formula here, you should be fine. And then you can tack onto it the square root of 0.490909, parentheses, 1 minus 0.490909, close parentheses, divided by n. I don't know why I didn't just write n in on the paper here. N was 1100. Close parentheses. There's a lot of parentheses going on here. And if you leave one open or close one too soon, you might mess this up. So hoping I typed in everything correctly, you should get 0.0283, something like that. Can anyone verify that that is what you got as well? That's what you got.
I just have a question. Sometimes the different calculator says area, and then
Area should say left.
okay. And then where would I put everything else?
Unfortunately, I'm blind as it gets, so.
That's what it looks like. When you pull up the end first.
Okay, that's a good question. So it says area this, mu is this, and sigma is that. Let me make sure I say this right. Keep your mean, so mu as 0 and your standard deviation is 1. That should come as default. If not, make sure it says, make sure your mean is 0 and your standard deviation is 1. Your area should be 1 minus 0.06 divided by 2. That should be your area. So that's a good question. Yes, so see if I can fit this on the screen somewhere. Yeah, so I keep forgetting there's some of you with fancier calculators. The area is 1 minus 0.06 divided by 2. Mu should be default at 0, and sigma should be default at 1.
And then we plug in the rest of the formula after we hit enter.
Yeah, I'm trying to remember. So once you enter all these values in, what comes up on your calculator?
I got like 2.8, negative 2.18.
I guess if I figure out yours, I'll figure out everybody else's.
Well, I'll put the whole formula in. 1 minus 0.06 divided by 2.
Yeah, so notice input what you have, and then you'd have to put the square root stuff after that. So, all right, let me accommodate this for all the fancier calculator people. Fancier calculator people, once you type in your area, your mean, your standard deviation, as I have it written here, once you paste, I think it says paste on there, and make sure it says left. If it asks you for a specific area, put left. Once you paste it, it will pop up on your screen almost exactly like I have it here. It's going to add some more stuff though. That's okay. Once it'll paste everything for you, and then you have to go in and put the square root part. So you have to put the square root part after that. So I'm glad you asked that question, because that applies to more than half of the people in this class, I believe. And if everyone types in everything just like that, you should get 0.0283, unless I typed in something wrong, which it seems fine on my end. Can a fancier calculator person confirm this is what you got? That's what you got. Okay, so I'm going to trust that. If not, I'll leave it to you to try to figure out what went wrong. But this is not the final answer. This is the error. They want the interval, the confidence interval. We know how to find the bounds now that we know the error. So we can find the lower bound, which is the point of estimate minus the error. And we can find the upper bound, which is the point estimate plus the error. So 0.490909 plus, or actually I'll do minus first, minus 0.0283. Again, I'm sort of picking these decimals arbitrarily. Maybe I should have rounded to 4 decimal places. So I'll put 49 here. So add that to your error. Just put the 49 at the end. I guess I'll be consistent here. So let's go back and try it again. 49. .46256 is the lower bound when you have the minus sign. And to get the upper bound, you just simply add. 519258. And this represents your confidence interval with a level of confidence of 94%. If you wanted a different level of confidence, you would get a different interval corresponding to that. So I'm definitely glad you asked that question. That was I have to remember that for my next class. Okay, does anyone have any questions? We're going to do something fairly similar here. If that seemed a little technical or confusing, we got, I think, 2 more examples here. That is fine. Let's move on to example 4. All right, so 1,013 adults were interviewed. 527 people supported the death penalty. They want us to find, really, they want us to start off by determining a point estimate. So the point estimate, well, we're not given the lower or the upper bounds, but we are given the ratio. It's 527 people that support this, support the death penalty out of 1,013 people. That's really it for part A here. I'll round this to, I'll do 6 decimal places. Again, I don't want to round too early and risk losing precision for my final answer. 520237. So part B, they want us to determine the 95% confidence interval for the population proportion. So basically, we're going to be doing what we did in the last problem. So I guess to sort of salvage what space I have, I can also just remind everybody that alpha, this isn't part A, but to remind everyone that alpha is based off of your confidence interval. we have a 95% confidence interval, and alpha is the complement of this confidence interval as a proportion. It's the complement, which means you subtract it from 1, or if it were a percentage, you would subtract it from 100. But you want to make sure your format is represented as a decimal ultimately. And from here, we know p hat, we know alpha, we know, what's the other one, n. So we can plug it straight into the formula. Because they want the interval, which means we need to know the bounds. But to figure out the bounds, we need the error. So really, I'm going to skip straight into the inverse norm of 1 minus 0.05 divided by 2. Just remember, that's what I had written up here. It's the square root of p hat, which we found to be 0.520237 times 1 minus 0.520237. All of this divided by lowercase n, which we had as 1013. So we can go ahead and plug all of this stuff in. Start off with the inverse norm. Definitely important though, you have the primitive calculator like what I have, definitely have to close your parenthesis. If you have the fancier one, it'll do it for you after you paste. And then we can multiply 520237, 1 minus 0.520237 divided by 1013. Zero 30765. I'll do 6 decimal places here. So that helps us find the error, but not the bounds. We have to simply do one more step to figure out the bounds here. The lower bound is equal to, that's p hat minus the error. And I'll do the upper bound all the way over here. P hat plus the error. So 0.520237 minus 0.030765. Get the first one. 489472. 0237 plus 0.030765. And that helps us find the other one. 551002. They might ask you to round to 4 decimal places. I'll keep 6 just in case. But one thing I do recommend though is you don't want to round too much on intermediate steps. If you have an answer that's not your final answer and it requires you to round, I recommend using more decimal places. The less ones you use, it will screw up your answer more later on because you lose precision each time you round. So 6 decimal places leading up to the final answer, and then maybe 4 at the end, or however many it asks for. I feel like that should be fine. So there's part A, and then part B really has 2 parts to it technically, the lower bound and the upper bound. So that's part B. Part C asks, is it possible that a supermajority, so basically more than 60% of adults, support the death penalty? Well, our 95% confidence interval goes from about 49% for the lower bound, all the way up to 55%. We are 95% certain that between 48.9% and 55% of United States citizens support the death penalty. Now, 60% is, of course, outside of that interval. Does that mean it cannot happen? Well, it's still possible, because with 95% confidence, that leaves 5% lack of confidence. So it's possible, but it's not likely. Since 60% is outside of the interval, well, really it's the confidence interval, from 0.489472 to 0.551002. That's what the confidence interval helps us interpret. 60% is kind of close to the upper bound. I mean, it's a little far off, but it could happen, because there's still that 5% lack of confidence, but it's not very likely because, well, we have a 95% confidence interval. Now, part D says construct a 95% confidence interval for the population proportion of adults who do not support the death penalty. We had a 95% confidence interval for adults who did support it. Now we need to figure it out for adults who did not support it. Now it turns out, for this flip-flop in how we look at this, really it works out pretty nicely. The lower and upper bound represent proportions, which are percentages. So really, the lower bound of this is 1 minus the upper bound of the original one. You might think, why the upper bound? I'll explain that in a second. And then the upper bound is 1 minus the original lower bound. Yeah, so you might be thinking, why am I switching these two? Well, the reason why ultimately comes down to what their values come out to be. 1 minus 0.551002 and 1 minus 0.489472 510528. Notice how when you subtract the larger number, you get the smaller number. When you subtract the smaller one, you get the larger number. So really, you don't have to use the formula again if you want to know the converse information. We figured out all this stuff about people who do support the death penalty. And with that, you could figure out, well, the complete opposite value, the people who do not support it. This comes down to the assumption that we deal with variables that are qualitative and only have two value outcomes. So really, that's the answer. That's part D right there. Don't have to do anything else. Does anyone have any questions before we look at the last problem for this section? There's one more formula that we need to, or actually two formulas that we need to shove in. And this is a sample size requirement. Now, this is ultimately, I mean, you can really apply confidence intervals to any collection of samples, but how reliable is that confidence interval? And what this is saying is, this gives us a formula to determine how many samples we need in order to trust our confidence interval. Because what would it mean to have a confidence interval when we're only given or only find two samples, just two samples? That's 2 samples, that's very small. That's very exclusive of the diversity of different things that could happen. So there's this formula, which is really just an algebraic revision of a previous formula we looked at. So there's this formula here. So notice n is what we're looking for in this formula, and everything else here should be familiar in terms of variables. And this is if you're given a confidence interval for P with a with the point estimate. So really this is if you're given a point estimate. The next formula is if you're not given a point estimate, which they kind of give you an arbitrary value of 0.0 or 0.25, but then the remainder of the formula follows. And they make you round up for some reason. I guess that makes sense, but I won't get into the specifics. So this is basically, what sample size do you need in order for your confidence intervals to actually be legitimate? In other words, based off of your error, your point estimate, and this very particular z-score. So let's break down example 5 and see how we can mix and match all of this to our formula. A sports network wants to estimate the proportion of Americans who follow professional football. What sample size should be obtained? So we are looking for n. If he wants to be within 3 percentage points with 95% confidence if he uses this previous estimate of 53%. So they're throwing a lot of percentages at us. 3 percentage points, 95% confidence, 53%. How do we make sense of all of this? So what is happening here? Well, 95% confidence will tell us alpha. Your confidence will always tell you alpha. Anything alpha is 1 minus 0.95, which is equal to 0.05. So we have alpha. So remember, we're looking at this formula up top here. And the reason why, so this is on the assumption that they're actually telling us a point estimate. Remember, the point estimate is a proportion, in this case, proportion of people who watch football. The proportion of people who watch football, they don't give us X or N, but they actually give us the ratio already. They tell us 53% of people watch football from this estimate, which is really 0.53. So basically they did the division for us. Instead of telling us that 53 out of 100 people watch football, they're just telling us the quotient itself. They just skipped a step for us. So what else do we need in this formula? We need the error. We need E. That's the last thing we need here. And then it says that they want the error to be within 3 percentage points. Well, 3 percentage points, that's 3% as a decimal, 0.03. And now we have all of our required values, which means we can use the formula. N is equal to 0.53, 1 minus 0.53. And this is where it might get a little tricky, because now they're asking for inverse norm. It's pretty much how I'm going to interpret that Z with the alpha divided by 2 notation of 1 minus alpha was 0.05 divided by 2 divided by 0.03 quantity squared. I know it's a fun formula, but it's very much calculator oriented. I'm going to plug it straight in. 0.53, 1 minus 0.53, close parentheses, open another parentheses. Now I need inverse norm. So go find inverse norm. 1 minus 0.05, oops, 5 divided by 2. Remember, your area, if you have a fancier calculator, is 1 minus 0.05 divided by 2. That is your area. And then however you end up getting inverse normal on your calculator, you keep going. Divided by 0.03, close parentheses, to the second power. I'm going to hang tight right fast and make sure everyone can catch up to this point. Did anyone get this number as well? You got it? Okay. You did not, be very careful about how you type this in. This is a parenthesis nightmare. I'm going to confirm based off of the small majority here that the answer comes up to be, well, initially 1063.23 blah, blah, blah. But sample sizes refer to objects, and objects are referring to Americans. So the number of Americans is a whole number. They force us, so I'm just giving you a warning right now, they're forcing us to round up. They're making us round up. So if you're wondering why, if you get into a MyMathLab issue where they're not accepting the rounded part, they're making you round up no matter what. So I know you would pick 1063, but they make you round up to 1064. I'm seeing a lot of eyebrows, twitch and confusion. So is there anybody having issues with this process? I'm going to assume that's my nearsightedness and hope that everyone's on the right track. Okay. So from here, part B, so we have one more part left. Part B says, what happens if there are no prior estimates being involved? Now, prior estimates, if a prior estimate of P is unavailable, use this formula. That's exactly what we're going to do. It's the same exact values. It's just a different formula. So I'll try and keep that formula above while I write in 0.25. So again, I'm following the formula on top of the screen here. This is when you don't have a point estimate. So then it says Z to the Z sub alpha divided by 2. So I'm going to use inverse norm again, which is going to be the exact same. Divided by the error of 0.03. Because that's still the error from before. And that's all squared. So it's fairly similar. In fact, I'm going to just take the results from before. If you press second and enter, you can bring back the results from before. And I'm just going to go all the way back and just press delete, delete, delete. 0.25, one more delete. And that should do it. So it doesn't change the number too much, but it does enough to give us, well, relative to MyMathLab, a completely different answer. 67.07, which they force us to round up to 1068. So leave that on the screen here. Yes, that does conclude this problem though. Now, if you're having any issues typing this in, I am about to go over the exam review. You can ask me after class if you're having any issues typing this into the calculator. Initially, though, does anyone have any questions before I move on to the exam 2 review? If not, then let's go ahead and, so again, for those of you virtual, when you come into class on Wednesday, I'll hand out the physical copies to you then. Let's go ahead, though, and pull up the exam here. So, as mentioned, okay.